We will start in a minute. Okay, let's start it. Other students will join in between, or they can watch the recorded video later. So today, what we are planning is we are going to solve questions from GATE 2019 question paper. So basically, initially I used to first tell you the concept and then solve questions. But today I have changed since I have to give the videos to the GATE and PTL as well. So I have to solve some GATE problem as well. So what we are planning is we will solve the concept in between whenever it comes as a part of GATE questions. So main focus will be on solving the questions and learning the concept in between rather than first concept and then solving the questions. Okay, so welcome everyone, and you can give the feedback in the last whether this way of teaching is good or not. So let's start it with this questions papers from GATE 2019. So there is this question number 16. It said that an infinitely long thin cylindrical shell has its axis coincide with the z-axis. It carries a surface charge density sigma naught cos phi, where phi is the polar angle and sigma naught is a constant. The magnitude of electric field inside the cylinder. So basically, we have given a infinitely long thin cylindrical shell, and it is said that there is a surface charge density that is around this surface of this cylinder, and we have to find what is the electric field inside the cylinder. So basically, the first thing that came to our mind after looking at this question is it's a cylindrical shell, and we know that whenever there is a shell, we whatever the charge we decide inside this cylinder, it will go at the surface. So if we try to solve this problem using Gauss's law and try to create, a Gaussian surface, there will be no charge inside the cylinder. So first thing that came to our mind is from Gauss's law that the electric field might be zero since Q enclosed inside is zero. But this is not the case with this particular system. Here look at the charge density. It is given by cosine sigma naught cos phi. So basically, what this question is, you have a cylinder and its axis lie along the z direction, and this is let's say xy, and this is the phi direction, phi that angle, polar angle, in cylindrical coordinate. So basically, we have r phi z. So our charge distribution is self-dependent on phi angle. So you have different charge at this angle of phi, but if you have another move towards the cylindrical axis, something like here, then you have another charge because your charge now depend on the angle phi. So in this case, the electric field is not going to zero, but how we can calculate it if we do not calculate it using Gauss's law. So whenever you are kind of stuck in this kind of situation that you are given a charge density and you have to calculate either the electric field or the potential, always try to go towards this formulation of Laplace equations. So basically, you do not have to drive the complete solution of Laplace equation. All you have to do is remember the solution. For example, what is the solution of the Laplace equation for a particular coordinate system? For example, Laplace equation said that del square V is zero, where del square is this divergence of gradient of V. So in Griffith book, or you can go through the NPTEL lecture, there is the solution of this Laplace equation in three coordinate system. Either you can go to Cartesian coordinate or spherical coordinate or the cylindrical coordinate. The solution of this Laplace equation is given and the potential has given what will be the form of potential. And using the boundary condition that is given in the questions, something like surface charge density or any other thing. If this condition is given to you, use that to calculate what is the actual value of potentials. For example, here we are given cylindrical system. So we are going to solve the Laplace equation in cylindrical coordinate. So basically, in this solution you can see in NPTEL lecture, or you can go through the Griffith chapter 3 or problem 3.4 exactly solve this problem of Laplace equations. So in Laplace, the Laplace equation in cylindrical coordinate is given by this 1 by s del by del s. This is the del square in cylindrical coordinate. So 1 by s del by del s del v by del s. I hope you are familiar with this del square v. Del square means in cylindrical coordinate system. So basically this is the Laplace equation in cylindrical coordinate. Then what they do is they separate into this variable. The variable that are dependent on s is separate differently, and the dependent on phi is separate differently. And then when we are trying to del by del s, only the components which are depend on s will decide inside the differentiation. The components that depend upon phi will go outside the differentiation. And when they are trying to solve it, they are left with only two this type of form in which one part is completely dependent on phi, another one completely dependent on s, and they put it equals to zero. And by solving that, the form of potential is turns out to be something like this. There are some constants which depend on s, and the dependence of phi is coming in the form of cosine and sine, and dependent on s is come in the form of s to the power k. K will can go from plus 1 to infinity. For cylindrical coordinate, it is from plus 1 to infinity, while for spherical coordinate, it is minus infinity. So this is the basic form of potential in cylindrical coordinate system. So from there, we will start solving our question. There are three forms we have to generally know. One, what is the form in cylindrical coordinate? What is the form in spherical coordinate? And what is the form in Cartesian coordinate? So we our form is come something like this, but we have so many variables like a naught, b naught, ak, bk, ck, dk. So we have to know what is these values to find what is our potential. And to know this value, we go to the boundary conditions. See, we have given that it has the cylindrical cell has a surface charge density sigma naught cos phi, and we already know that the boundary conditions I have talked in previous lectures. If we have a surface and there is a surface and there is a above to the surface there is a point, and below to the surface there is a point. Then electric will have a discontinuity at the surface if the surface carries charge density sigma, and the perpendicular component is discontinuous by sigma upon epsilon naught, while parallel component will remain continuous. This form can also be written into the form of vector form like E vector above minus E vector below equals to sigma upon epsilon naught n cap, where n cap is the direction perpendicular to the surface. So since the parallel component will lie perpendicularly, so when we multiply this term will become zero. So only this component will have sigma upon epsilon naught. For parallel component, this term is zero. So these two combined form can be written like this. And we already know that the electric field is given by negative gradient of V vector. So when we put this into this equation, we are left with gradient of V above minus gradient of V below equals to sigma upon epsilon, negative sigma upon epsilon naught n cap. So the gradient that is survive is in the n cap direction. Other directions will become equals to zero. Like if we take any other direction which is perpendicular to n cap, this will become del V above upon del V something other direction like k. I suppose there is some direction k and which is perpendicular to n cap. So we are left with del V by del k above minus del V by del k below equals to 0. So basically that will eventually give me like V above equals to V below. That is potential is continuous across the surface. So this and however for the case when there is an n cap direction, this term survive. So the gradient of potential is also get discontinuous by this quantity negative of epsilon naught, as long as gradient is in n cap direction, which is the direction perpendicular to the surface. So these are the two boundary conditions we have. Gradient is discontinuous and the potential is continuous. So now we started with this our equation. This one. See, the equation have three parts. If we look closely, it has this one part, which is generally independent of phi, mod of like a constant. This part, which contain s to the power k, and this part which contain 1 by sk. So if you are trying to calculate the potential inside this cylinder, you have two resin. One is the inside and another one is the outside. So S can vary from 0 to infinity. So how much radius we can go, or 0 to R, the maximum radius of the cylinder. So inside resin, it can go 0 to R. So if we put S equals to 0 in this in this part of the equation, 1 by 0, this will become undefined, and also log of 0 will become undefined. So these two quantity, B naught lns and this one, they are not going to survive for the inside potential. So the for the potential, if we are trying to calculate inside the cylinder, only the term that is surviving is A naught and this one, where we can put S equals to 0. And we are talking about the outside case. Then we have B naught LNS with just I put, A naught bar and 1 by SK since SK will start after R to infinity. So this term is also going to survive and this term. So we have two potential, one is inside and another one is outside. And it is similar to like above and below. You can consider below as inside part of the cylinder and above as the outside part of the cylinder. And we have to use these boundary conditions. So from the first boundary conditions, we have del V out by del S. I have just changed above to out and below to in. So basically del V out by del S. S is just the radial direction. So del V by at surface R. So if you look at the cylinder, we have to apply all the boundary condition across the surface. So we have del V out by del S, del V in by del S at S equals to R equals to sigma upon epsilon naught. So we have given sigma as sigma naught cos phi. That is already given. I take minus epsilon naught this side, and I have differentiated the outside part with respect to S. So if I take my potential V outside and we differentiate it with respect to S, this term will become 0. This term will become summation over k equals to 1 to infinity minus k sk plus 1, and this term will remain as it is because it is independent of S. So when I put S is equals to R, this is the term that is remain outside minus del V in by del S. So if I take del V in and I differentiate it with respect to S, we are left with k sk minus 1, and this term will remain as it is. So if you look at k rk minus 1, here I have put S is equals to capital R because we are talking at the boundary surface. So basically this is come after applying these boundary conditions. Now, whenever you're trying to solve the equation using this Laplace equations formulation, once you reach this step, all you have to do is just try to equate the coefficients of left hand side and right hand side. See, on the left hand side, you have sigma naught cos phi. So basically, you have only the cosines part on the left hand side. So on the right hand side, there should be cosine part. So all the coefficient corresponding to sine component has to be 0. So we put dk and bk 0. And also the argument of cosine is just 5. That means what is our potential V? So another boundary condition that V is continuous at S equals to R. That means V out at S equals to R equals to V in S equals to R. So we put this equation equals to this equation. Now we have known that K is equals to 1 and BK decay is 0. So we put this thing here. So we are left with A naught RA1 cos phi A naught bars C1 cos phi by putting this K equals to 1. Now again we create the coefficient of cos phi. We are left with RA1 equals to C1 R. So A1 is equals to C1 R square. So we will get this relation we put into this equation for further, and when we put this into equation we will get the value of C1. So C1 is equals to sigma naught R square upon 2 epsilon naught. So C1 value is then computed in terms of non-coefficients. And when we put back C1 into this equation, we get A1 in terms of non-coefficients. So our V in is equals to when we put back this into this equation, we put K1, VK, DK 0 and put the value of C1, V1. Our potential V in will become SA1 plus A naught, and there is a quantity plus A naught bar. V in. Actually, we are just talking about V in. V out, we are not talking since we are only interested in electric field inside. So electric field inside is negative gradient of V in. So we take the gradient of V in. So this is our V in. So when we take in cylindrical coordinate, we are talking about gradient which is del by del S of V in the escape direction plus 1 by S del by del phi of phi cap and del V by del Z in Z cap. So when we do that, This is our electric field in S cap direction. This is electric field in phi cap direction. So this is the total electric field inside. So in the question we have been asked what is the magnitude of that. So we take the square root of this term square and this term square. So this will give you the magnitude of electric field as sigma naught upon 2 epsilon naught. So it is given in the questions, I guess. Sigma naught upon 2 epsilon naught. So this is the answer for this question. So this problem is also solved for spherical coordinate system in Griffith. Or you can go through this NPTEL lecture for more information. But I hope you will get clear. You have to start the questions from the potential equation and you apply the boundary condition. Basically, you have to equate the left hand side and right hand side and then apply these boundary conditions too. I hope you are clear with this question. If you have any doubt, you can ask. Or we can move to next question. Shall we move? Okay, I'll move to next question. This is the question number 19. A circular loop made up of three thin wire has a radius of 2 centimeter and a resistance of 2 ohm. It is placed perpendicular to the uniform magnetic field of magnitude 0.01 Tesla. At time t equals to 0, the magnetic field starts decaying, where T0 is given to be 1 second. The total charge that passes through the cross sections of the wire during the decay is Q. What is the value of Q? So basically, this question, in this question, magnetic field is changing, and it is known from Faraday's law. Whenever there is a change in magnetic field or there is a change in area, that will lead to the change in magnetic flux, and the change in magnetic field always lead to the flow of current, and that flow of current will generate a magnetic field that will try to reduce the effect of this change. So basically, this type of questions is based on Faraday's law. So whenever you see that there is a change in magnetic field or there is a change in area, you always going towards this Faraday's law because it will change the magnetic flux. And whenever there is a change in magnetic flux, there will be an induction of the current. So to get the more information regarding the Faraday's law, you can go to the NPTEL lecture. The link is also given here. So basically what is given in this question is there is a magnetic field which is changing with this form and there is a loop, closed loop which is placed inside this magnetic field. So as the magnetic field starts changing, there is a current that is start flowing inside this loop. And due to this current flow, there is a charge is also flowing since current is the rate of change of charge flow. So we have to find what is the total charge Q that is flow in the infinite time because total charge will flow in infinite time. Okay, so to calculate the total charge, we must know what is the current I that is start flowing due to the change in magnetic field. And the current I is given by voltage V upon resistance R or EMF E upon resistance R. So to calculate the EMF, it is given by rate of change of magnetic flux, which is minus del phi B by del T, which is phi B is magnetic flux, which is given by surface integral of B dot dA. So here magnetic field B and the area vector due to this loop, they are both in same directions. So B dot dA will give you B mod B into mod dA. And when you try to integrate that, B will come out. Mod B is simply B naught. And integral of dA will give you BA. So phi B is equals to B into A. And with EMF is equals to del phi b by del t. A is constant. Area of the loop is not changing. So B will come, A will come out of the integral and you have to differentiate B. T is a function of time t. B naught a to the power minus t by t naught. So when you differentiate it, area is given by pi r square, where r is the radius of the loop. T naught is given to us 0.01 Tesla. T naught is 1 second and e to the power minus t by t naught. So basically, we have known E as a function of t. And so basically, we also know I, which is EMF upon R. We can calculate the EMF, they are saying. Yes, by putting the value of pi R, V naught, R is 2 centimeter, V naught 0.01 Tesla, T naught 1 second. So this is my E. I is given by dq by dt, which is EMF upon R. So dq equals to EMF upon R. R is the resistance. So our resistance is 2 ohm. So this is the dq. And to calculate the total charge Q, we integrate it over infinite time t. So 0 to infinity. When we integrate it, this quantity will come outside and there's this minus charge. I hope you know how to integrate exponential functions. So e to the power minus infinity is 0 and e to the power 0 is 1. So total charge comes out to be 6.28, that is power minus 6 coulomb. So basically, this question is based on this concept of Reddy's law. You just have to understand that the change in magnetic field will induce a current, and that current is a rate of change of charge, and from that you will calculate what is the total charge Q. I hope this question is clear to you. Is so next move to the next question. The electric field of an electromagnetic wave in a vacuum is given by E equals to E naught cos 3y plus 4z minus omega t. Omega is 1.5 10 raised to power 9. So this is the electric field which is polarized in x cap direction and it has its own propagation vector in yz plane. So the wave is reflected from z equals to 0 surface. That means the wave is propagating in the yz plane, but it reflected from z equals to 0, that is xy plane. So if the pressure existed on the surface is given by this, what is the value of alpha? So the question is, we have a surface in xy plane. So in the xy plane, we have placed a surface. And the propagation vector can be calculated, if you equate this equation with the general form, E naught cos k vector dot r minus omega t. So k vector will give you 3y cap plus 4j cap from this, or you can calculate k vector as gradient of this k dot r. So this is your k vector. So the propagation vector is in yz plane. So you have some wave which is traveling something like this, and it is reflected from this xy plane, and it will go like this. And this wave is polarized in x direction, and exert this plane then exert a force onto this plane, and we have to find what is the force, what is the pressure that is exerted due to this force. So pressure is generally given by 2ic cos theta, where theta is the angle between normal to this surface and the propagation vector of this wave is making. So normal to the surface is the z direction, and this is the propagation vector direction, k cap direction. So the angle theta is between k cap and z cap direction. So there are two ways you can solve this problem. Basically, you have to find what is this angle cos theta. So one way is you just take your k vector and use the formula of cos theta, which says that k cap dot z cap will give you cos theta as you project your propagation vector in the z cap direction. Another way is You already know this angle theta. Your k vector is given by 3 in the y cap direction plus 4 in the z cap direction. So if you make an triangle, so tan theta will give you how much it is. In the y direction, it is 3, and in the z direction, it is 4. So this is 4, this is 3. So this is your tan theta. So you have to find what is the cos theta. So basically, you create a right angle triangle. This is theta, and 3, 4. And for finding cos, this is 5. This is generally Pythagoras theorem. Then cos theta is equals to 4 by 5. So this is generally simple calculation, and you have to calculate pressure P, which is 2I by C cos theta. So you put the value of cos theta 2I by C 4 by 5, so 8 by 5 IC. I is the intensity which is given by average of the Poynting vector, which is equals to 1 by 2 C epsilon naught E naught square. You can go through 10 PTL lecture. Actually, I haven't provided you the link here, which solve this derivation for Poynting vector. So by taking the intensity I as 1 by 2 C epsilon naught E naught square and I by C, this quantity will cancel out. So this is the term that you are left with. Alpha is then turns out to be 4 by 5. So the value of alpha is 0.8. So the answer is this. So this is the question number 20. It will be useful if you remember the intensity I is given by 1 by 2 C epsilon naught E square, because there are a lot of questions that is based on only this formula. In previous gate year, there are a lot of questions that is coming. So it will be useful to you if you remember that. So I hope this is clear. Now next move to this question. A solid cylinder of radius r has a total charge q distributed uniformly over its volume. It is rotating about its axis with angular speed omega. The magnitude of total magnetic moment of the cylinder is. Now we have to find what is the total magnetic moment of the cylinder. But the question seems, initially confusing. Like you are given a solid cylinder with a total charge q that is uniformly distributed over this volume and it is rotating. Then they ask what is the magnetic moment. So how the concept first, we have to know how the concept of this magnetic moment come here. So this concept I will try to let understand what is happening here. And for more detail, you can go to NPTEL lecture. But the basic concept I will tell you. So what is happening here is you're already familiar with this electrostatic concept, which says that if there is a current that is flowing, not electrostatic, magnetic concept, which says that if there is a current that is flowing in a wire, then you can always feel a current magnetic field. You always feel a magnetic field in the nearby region. And the direction of magnetic field can be calculated if you place your thumb, right hand thumb along the direction of current and curl your finger. Then this your finger will give you the direction of magnetic field along this wire. Now you already know that the current is nothing plus is the flow of charges. There is a flow of charges that lead to currents and therefore magnetic field. So in this case also the charge q is also flowing, but it is flowing in omega direction. If this is the direction z cap and this is the direction in which the angular velocity is also pointing in the z direction. So you have a uniform cylinder. The charge is distributed. So you have lots of charges here within this volume, and each of them are rotated. So whenever there is a moving of charges, it will lead to current, and the current will lead to magnetic field. And another interesting concept here is the current that is created by the circular loop. If there is a current that is flowing in circular loop, it will lead to magnetic field that will resemble exactly like the magnetic field of, dipole moment, dipole. So you know how the magnetic field of magnetic dipole look like? It is look like this. You have a magnetic dipole. It's have north direction and south direction. So magnetic field lines are originated from north going towards the south. So if you take a circular current carrying loop in this, now the loop is something like this. Now if you wanted to know how the magnetic field lines are going in the circular loop, just take out this one small part. And now the current is flowing like this. Point your thumb in the direction of current and curl your finger. So you can see that for this small tiny part, the magnetic field lines are like this. Similarly, if you take this, actually it is, and in this case, the magnetic field line in opposite direction. So basically, if you try to visualize it, this is how the magnetic field line look like due to this circular charge moving. So they are both basically both are the same. So if your loop is very tiny, then it will resemble very much like a magnetic field due to a dipole. So here the current is flowing in this circular direction, and this circular direction is kind of creating a circular loop, and therefore the field that is created by them is very much like the magnetic field that is created by these dipoles. So we have to find what is the total magnetic moment that is created by this movement of charges. So basically, the way to solve this problem is take a slice of this charge distribution. So if you slice this, you are left with a charge distribution, something like this. Yeah, I have done there. So the charge distribution is in the form of disk, and this charge distribution is rotating in the with angular velocity omega. So the current is the surface current because it is the charge density is over the whole surface. So the formula to calculate what is the current that if there is a line charge density lambda and it is moving with velocity v, the current is given by lambda into v vector. Similarly, for the case of surface current, k vector is given by sigma into v vector. The sigma is the charge density, which is given by q upon a, and v is the velocity, which is moving, with which the charge is moving. But here it is rotating. So v vector is given by omega cross r, the general formula relation between v and angular velocity. So we have to know what is the surface charge K. So V vector is given by omega cross R. Omega is in Z cap direction, radius R is in R cap, and in cylindrical coordinate, Z cap cross R cap is given by phi cap direction. So well, K vector is given in the form of phi cap. So basically, your surface current is circular. This is the phi cap direction. So we have to calculate magnetic moment. It is given by this formula. 1 by 2 r cross k into dA vector. Generally, magnetic moment for very simpler case is given by I integral of dA, but here in this case it is given by this formula. It has to be derived, but the derivation is given in which book. I haven't taken it here. So basically, we have to calculate what is r cross k. We know k, r is simply r into r cap. So we just take r and k sigma omega r cap cross phi cap. And r cap cross phi cap in cylindrical coordinate will give you z cap direction. So your magnetic moment is given by 1 by 2 sigma omega r square dA. dA vector in z cap directions. Only then r cross k and dA will become. Now it is in z cap, so dA has to be in z cap. So dA in z cap is given by r dr t phi in the z cap direction in cylindrical coordinate. So d phi can go from 0 to 2 pi, r can go from whole radius 0 to r. So we take this, integrate this quantity, and we are left with this magnetic moment 1 by 4 sigma omega. But the answer is given in the form of Q. So we have to bring our Q back. We know that sigma is given by Q upon area. So basically, Q is equals to sigma into pi r square. So sigma into pi r square will give you Q. So magnetic moment is given by 1 by 4 Q omega r square. So this is the answer 1 by 4 Q omega r square. So this NPTEL lecture also given the magnetic dipole moment for what if the spherical shell is rotating instead of cylindrical shell. So it will be useful if you go through this NPTEL lecture. So with that is question is finished. This one is the last question. It's a formula based question, basically. The vector potential inside a solid long solenoid with n turns per unit length and carrying a current I. Written is lengthy. So basically you are given a vector potential. If some another term is added to this vector potential, what is the magnet and the magnetic field will remain same. What is the relation between alpha and beta? So basically they have some A vector and corresponding to that there is some magnetic field. Now what do is they change here A vector to some another term. They add another term to them and their magnetic field still remain the same. So they have to find what is the relation between alpha and beta. See, the formula is a formula based question. We already know that the magnetic field B is given by curl of A vector. And generally, when we are trying to solve the questions which are based on solenoid, either we use the differential form or we use the integral form. We say that closed integral of P dot dA is equals to line integral of A dot dl. So generally these two formulas are used when we are trying to solve problems which are based on solenoid. So we are going to use differential form here. We are given that we are given A vector, which is mu naught Ni by 2 S in the phi care. Now there is another term A naught, which they are added to A so that the magnetic field will still remain same. So what is the magnetic field with respect to A? So we calculate the curl of A and it is in cylindrical coordinate. So this is the curl in cylindrical coordinate. This is how it is calculated. I hope you know how to calculate the curl in cylindrical coordinate. And if you know the vector A is in the phi cap, so only A phi component is survive, AR is 0. And when we do the differentiation with respect to R, this term 0. When you take with respect to phi, this term 0. Only Z cap component, that magnetic field will give in Z cap. Now you have to calculate another magnetic field which is coming after adding another component to that. Since curl can be distributed, so we have curl of A naught. We already calculated curl of A, so we can use it later. We just calculate curl of A naught. So curl of A naught is calculated. A naught will contain both components, phi cap and S cap. So we have phi cap and S cap that component. And once it is solved, this is the component of magnetic field comes in the Z cap direction. Now they have to add mu naught Ni as well for the curl of A, and this will give the same magnetic field mu naught Ni. So this term will cancel out. So we are left with this term equals to 0 and This will give you alpha cos phi equals to beta by 2 cos phi. And just cos phi again cancel and alpha equals to beta by 2. So this relation between alpha and beta is alpha equals to beta by 2. So with that, today's question got finished. So if you have any doubts, you can ask. You or just give me feedback. You find this way of solving questions is better or the previous one is better?
My previous one is better.
Means first teaching the concept and then all the questions that is coming in previous gate year related to that concept is solved.
Yes, ma'am.
Yeah.
Our previous one was better.
Okay, I will go back to the previous one then. Actually, we have been taught to, we have to find the gate questions and solve them. But I will go back to my previous one. But just tell me, are you able to get the whatever I teach today, or it is hard since concept got mixed?
Yeah, it little bit hard.
Okay, since concept are different in every
Mm,
question.
yeah.
Okay, I will go back to previous one then. If any other doubt, okay. If you do not have any doubt, then we will close today's class.
Ma'am, can you explain question number one?
Okay, this one.
Yeah.
Okay, in this question, we have been given that we have a long cylinder and it's a shell. So we already know the property of a shell that whenever there is a charge placed inside the cylinder, it will go at the surface. And we are given a charge density which is dependent on phi angle. So basically, our charge is kind of dependent on at which angle our across the cylindrical surface the charge is vary with a cosine function. So we have to find the electric field inside the cylinder. So all these kinds of problem are solved by Laplace equations. And there are three problems that are generally came across this kind of issue. One is with cylinder that I have solved today. Another problem that will be come with spherical cell that is also possible. In that case, you have to solve the Laplace equation in spherical coordinate. And another one will be case when you have sheets. In that case, you have to go to Cartesian coordinate system. So here, as I've shown, when we solve the Laplace equation in cylindrical coordinate, this is the form of the potential that we are going to get. Similarly, we are also going to get the different form if we go back and solve the equation in Cartesian coordinate, and it will solve it in spherical coordinate. So all the three type of solution will be given to us for the potential. So we have to start solving our questions with this form. And this form will have lots of variables like AK, BK, CK, DK, A naught, B naught. So to get the values of these so that our potential will not be in the form of variable, we use the boundary condition that is given to us. We have given the boundary condition at the surface. There is a charge density. So boundary condition that we are going to use. So we have to divide our potential into two regimes. One is inside the surface, another one is outside the surface. And for the case of inside, S can be zero. So only those components which for which S equals to zero is not going to define, they will go with the outside component. And for the component which is they'll definite for S equals to zero, they will go with the inside component. So this complete potential will get into two parts. Half of it is in the inside part and half of it is in outside part. And using the boundary conditions, we are trying to equate these components inside and outside. And the boundary condition that we are going to use is the one that I have taught initially, which says that the electric field is discontinuous at the surface, from which we find that the gradient of potential is discontinuous at the surface. And normal potential is continuous at the boundary. So if we take two boundary conditions, the potential is continuous, but its gradient is discontinuous by sigma upon epsilon naught. So when we try to take the gradient of potential for the inside part and the outside part, subtract it, and then put it equals to the given surface charge density sigma naught. And once we reach that situation, we have to equate the left and right hand side. From there, we will calculate what is the variable values. For example, the left hand side does not have any sign. So all the sign component will become zero. There is only cosine part is there. Therefore, the cosine part will going to survive, but its argument is 1, cosine 1 phi. So k value has to be 1. So using that, we are left with C, k equals to 1, dk, bk 0, C1 and A1 is survived. All other components like C2, C3, all are 0. Similarly, A2, A3s are 0. So this equation, which initially seems like so big, is reduced to this form only. Now we have to find what is the value of C1 and A1 in terms of sigma naught, because this is what given to us. So to calculate that, we use another boundary condition that the potential is continuous at the surface. We put three outside part and inside part equal. We put the dk with dk 0. We also put k equals to 1. And using that, we are left with this equation. Again, we are equate the cosine component. From there, we find the relation between A1, C1. And when we put A1 equals to C1 upon R square in this equation, we are left with 2C1 upon R square into cosine phi. So when we put that 2C1 upon R square, we are get value of C1 in terms of non-coefficient. Similarly, value of A1 in terms of non-coefficient. Now we have to find what is the electric field inside the cylinder. And in this case, we are just concentrate our potential, what is inside potential. So we have just only A1 since our potential inside potential is this. Here K has to be 1, Bk is 0. So we have just A1 cos phi and S plus A naught. So this is our inside potential. We use that, we are left with inside potential. Then we differentiate it and taking the gradient in cylindrical coordinate. So this is the gradient. We differentiate it with respect to S. We differentiate it with respect to phi. But they ask, and this is the electric field that is turns out to be after this. They have asked for the gradient magnitude of this electric field. So magnitude of electric field is square root of ES component plus E phi component. So this is the magnitude of electric field. So basically all these problems have the same pattern. You start with this formulation and you apply the inside, find the inside and outside component and then apply boundary conditions. So basically it's the boundary conditions that is going to differ and change your answer every time. Otherwise, the way the problem is going to solve is same. Are you able to
Thank
get
you.
it?
Thank you, ma'am. Yeah.
The question is solved for the spherical shell in Griffith book or in this NPTEL lecture. You can go through that. Okay then. Any other doubt?
No, ma'am.
Okay, thank you. We will go back to our initial way of doing things next time.
Okay, thank you, ma'am.